Hi, my name is Samhita Pendyal. I'm a freshman at the College of William and Mary, and I did my research on improving machine-generated discoveries using unsupervised machine learning. This research was done at Virginia Commonwealth University in the Natural Language Processing Lab under Dr. Bridget McInnes and Sam Henry. Before we start, here's some important terms used throughout this presentation. Natural language processing is basically the ability for a computer to recognize human language as it's supposed to mean. The corpus is just a collection of texts. Clustering is the process of grouping together similar terms in natural language processing. Data mining is the examination of datasets to discover and understand new patterns. And unsupervised machine learning is a machine learning algorithm used to draw inferences from datasets without labeled responses. So now that we know those things about natural language processing, what exactly is literature-based discovery? Well, literature-based discovery is a subfield of natural language processing that seeks to uncover new information from already existing data. In literature-based discovery, you have an explicit A implies B relationship, an explicit B implies C relationship, and then from those two explicit relationships, you can then implicitly infer that A implies C. Take, for example, Raynaud's disease, a disease that causes blood vessels to narrow in some parts of your body, causing your body to feel numb in response to cold temperatures and stress. Through literature-based discovery, we can find an explicitly defined relationship between Raynaud's disease, the A term, and blood viscosity, the B term, in certain corpi, and another explicitly defined relationship between blood viscosity, still the B term, and EPA, the C term. And then from those two explicitly defined relationships, the computer can then infer a relationship between the A and the C term, or Raynaud's disease, and EPA. The prior methods of LBD worked extremely well when dealing with smaller amounts of literature. However, abstracts and new papers are being published constantly, therefore constantly increasing the size of the corpi. And thus, when you increase the size of the corpi, there tends to be an issue with the ranking of your target terms. You may have terms have similar definitions, but are ranked differently. This causes the accuracy of LBD to decrease. Therefore, the null hypothesis in this experiment was that if clustering does not improve performance, then the evaluation metric of discovery replication will not improve. To the right, you can see a 2D rendition of clustering. The points, which stand for individual terms, are grouped together based on how similar they are, each color meaning a different cluster. My contribution to LBD is highlighted in orange. The first part of the process in LBD would remain the same. The data would still be collected from Medline, which is considered your corpus, and then be put into a co-occurrence matrix, and then from there, the LBD would be performed, and then the target terms would be determined. However, usually after the target terms are determined, they're assigned a rank. I want to change that by grouping together similar terms and therefore performing the clustering. Once the clusters are completed, they are then visualized using D3 and they are assigned new ranks and evaluated. It's the same dataset used by Dr. Swanson in finding the relationship between Raynaud's disease and fish oil. The clustering is done using the Cluedo package, which consists of 5 different clustering algorithms. RB, which stands for repeated bisection, and that's when you have one cluster and you work your way down to the desired number of clusters. RBR, which is just repeated bisection with a global component. Agglomerative or agglo, which is when you start out with each individual term in its own cluster and you work your way up. Graph, which draws vectors of the terms and groups it together based on the vectors. And then direct, which clusters everything at once. Something else that should be noted is that the ideal percentage of clusters is not known because no research has been done, and therefore I increased it by 5% each time. And then after the clustering is performed, they are visualized using D3, and then they are evaluated using a t-test. In this experiment, we are able to reject the null hypothesis, as all the alpha values were less than 0.05 when compared to the baseline. Also, something else that should be noted is that the percentage of clusterings versus the target term rank is that at 40%, the effectiveness of clustering decreases. Something else that is important is the visualization aspect of clustering, and as you can see, the unclustered versus clustered version, you can see all the clustered terms, and in the unclustered version, it's very hard to tell which words are related to which. But in the clustered version, you are able to see each independent subgroup, and you're able to see which word is in the middle. Clustering is still a relatively new concept to LBD, and therefore it has a lot of future trajectories. Something else to test the effectiveness of LBD is to use a different evaluation metric. So instead of using Raynaud's disease and fish oil, something else could be used. There could also be a different distance metric used, so the co-occurrence matrix would be different. There could also be different percentage increments, so instead of starting out with 5% each time and going all the way up to 100, it could be a smaller percentage increment up until 40, since we know that 40 is when clustering stops working. And in the future, this clustering technology in LBD could be used in clinical settings. Doctors could use this to find new prescriptions or to try out new drugs for different ailments that they would not have necessarily thought about. I'd like to thank you all so much for listening to my presentation, and I hope you have a nice day. Thank you.